Hello everyone, I'm Chuanqi Zhang. I'm glad to introduce our paper about discovering the real association, multimodal causal reasoning in video question answering. Existing video question answering methods focus on feature extraction and feature fusion, while ignoring the statistical bias of the multimodal data. For video data, objects, background, and actions appear in the video. Which one is clue to the problem? For textual data, when the answer is a paragraph, can keywords represent sentence semantics? If the model ignores these questions, then the model trained on the collected data will give wrong answer. In this paper, we discuss the causal relationship in vision and text, and use a trainable model to judge whether features in the data are causally related or irrelevant. This judgment will be used to generate more meaningful data for the video question answering task. Video question answering aims to understand video information and describe it in language question-answer format. We show the simple in-causal video QA dataset. It provides the tagging of key persons in the video. The asked questions include description, explanation, prediction, and counterfactual questions. Recent methods focus on the explicit challenges of the task, including textual feature extraction, video feature extraction, and video text alignment and fusion. Especially in the feature alignment direction, existing works use different strategies to align and capture question-related features. Memory networks can prioritize the multi-step reasoning idea to refine the answer gradually, which is a great progress compared with early work. Transformer achieves total performance on several datasets, with the cross-model learning ability and the large circle dataset. Graph neural networks show promising results on inference tasks, with good ability of reason modeling. But their frameworks reason the answer relying on statistical evidence cues, which ignores potential bias in the multimodal data. It is simple. Two people are playing cricket indoors, and there are other objects in the room, including a TV that is on. If relying on the statistical relationship, the model may be confused by two value factors of indoor and television, and misjudge the concerned event, that is singing karaoke. Based on the clues provided by the question, the concerned event is related to the action that is taking place, which is two men playing cricket. This requires the model to accurately judge the objects involved in the event, and infer the answer. Besides, we show the selection deviation caused by statistical bias in the text. When inferring the reasons for answer selection, existing models intensively rely on correlations between local words and the video content. In this simple, someone to help is more related to the question and the video. But this reason has an unreasonable inference as the first part of the sentence. That is, a lot of people here. Therefore, simple local attention introduces new bias. Based on this observation, we formalize cross-model causality for the video QA task with a structured causal model. Gray variables are observed data. V is a specific video and S is a specific sentence. D represents the data domain, determined by the collected dataset. It causes the co-occurring of objects in the video V and various words in the sentence and answer label Y. The ideal causal inference is that model extracts video event features EV from videos and text event features ES from words. Then the model integrates different model event representations and filters out the event of interest E for answer selection 1. Here, we provide the backdoor adjustment from D to V and from D to S, which produces our architecture. That is the value causal model and the textual causal model. The first one is the value causal model. Before the appearance information and motion information are sent to the backbone for question answering, we propose a value causal model to find object-level causal features and the spurious value features. The image-level value features are first divided into object-level value features by the detected bounding box. The category information, location information, and the interaction relationship of each object are modeled by interaction detector. According to the question prompt, the indicator judges whether features are causally related or irrelevant. The uniform representation of causal and irrelevant features are used for further prediction in the VideoQuestion backbone. The second one is the textual causal model. As we discussed in previous, keywords sometimes introduce new bias. Therefore, we select the keywords according to the question and the vision alignment feature. Then, they are sent to the intervener to combine with other candidates in this question to generate new candidates. These new candidates will reduce the model's direct dependency on keywords. Two symbols here show the quantitative comparison between our MCR and B2A. In the example on the left, B2A chooses the third answer because both the body pose of the human and the environment are related to the lecture. Our method can find more specific object features and the spatiotemporal motion feature to get the correct answer. As you can see in the diagram below, MCR helps B2A improve the competence on the correct feature. In the right example, B2A is confused by the correlation between third in the text and the three bottles in the video. According to the causal object selection, MCR effectively arrives a low score for it. These examples demonstrate that our model can perform real and generalizable reasoning. More samples can be found in our paper. In summary, our contributions include discovering two new types of causal changes in multimodal data and proposing effective strategies to discover causal associations. Thanks for watching. That's all.